Hey everybody, this is going to be the study guide for Unit 10, which is all about infinite series and sequences. This, again, just like Unit 8, is a BC only tested topic this year. And in general, Unit 10 is only on the BC test anyway. This year, the Unit 10 is modified. Not all of the topics in Unit 10 are covered on the test. They only handpicked a few major ones. And I've written the section number down next to each of the heading. So geometric series is 10.2, for example, and then you can see the other numbers for the other sections. There were only 5 sections selected from Unit 10, and so this study guide will be pretty straightforward. It's based on the section. So this unit is all about determining if a series is convergent or divergent, more or less. And so there's different types of series based on how they look. So in each of these boxes, I've drawn or I've written down what the summation looks like, how you can recognize it on the test. So for example, this first box, geometric series, is in this format right here. The summation will usually start at n equals 0 or n equals 1 sometimes, but you want the geometric series to start at n equals 0 here. Your a value is some constant. R is what we call a ratio, and n is the exponent, and that's increasing by 1 each time you write a new term in your series of terms. So this would kind of look like a and r would stay the same in each of the terms. The only thing that would be changing is n. N would be increasing by 1 each time, starting from 0. So it would be 0, 1, 2, 3, 4, so on and so forth. And so there's a way to determine if, when you add up all of these terms, does that sum diverge, meaning does it continue to just grow larger and larger, or does that sum of terms, does it converge to some value? Does it get closer and closer and approach some value? So this is what this unit is all about: divergence or convergence of a series. And so based on what type of series it is, there's a different test or a different way you can check whether the series will diverge or converge. Diverge just or converge. So a geometric series, you can determine if it's divergent or if it's convergent based on these following things. So if it is divergent, then your ratio, the absolute value of your ratio, so I'll put absolute value of the ratio, your series is divergent if that number keeps growing larger and larger. So that means your ratio has to be greater than 1. So I'm going to put right here the absolute value of r is greater than 1, because sometimes you can have a negative ratio and it just grows largely in the negative way. So that's why there's an absolute value bar right there. So absolute value of r is greater than or equal to 1. Sorry. And then for convergence, it's going to be strictly less than 1. The absolute value of r is strictly less than 1. And that will give you a convergent series. And if you find that the ratio, absolute value of it, is less than 1, you know it's going to be convergent. If you want to figure out what value your series is convergent to, that's determined using this quick formula. The sum is equal to the a value divided by 1 minus r. That's how you find the sum very quickly. The a is just you pull the number from there, the ratio you pull from there, you figure out this fraction, there's your sum. Okay, the next type of series is called p-series, and a specific type of p-series is called harmonic series. So in p-series, your summation will look like this. It'll be usually 1 divided by n to the power of some power. Now in this series of terms being added up, your base here, n, is increasing, 1, 2, 3, 4, 5. But your power, p, is a certain specific number or value. And based on that value for p, you can tell if it's divergent or convergent. So for a p-series, if p is less than 1, is between 0 and 1, if p is less than or equal to 1, then you have a divergent series, meaning the sum of all the terms will continue to grow larger and larger. And the reason for that is because if you think about, if you had a fraction that's less than 1 here, or a decimal, if you take something to the power of that, this guy right here, the denominator is getting smaller and smaller. And if I divide by something that's getting smaller and smaller, my actual term is getting larger and larger because I'm dividing by something that's getting smaller and smaller. I'm dividing by a very small number that's less than 1. And so that's why if p is less than or equal to 1, you have a divergent p-series. And then you have convergence if it's the other way around. P is greater than or equal to 1. If your power, the p stands for power, if the power of the denominator is greater than 1, then you'll have a convergent series up here. And harmonic series, so over off to the side, I'll write that harmonic is when p is equal to 1. That's what harmonic means. A harmonic series is always going to be divergent. Okay, so there's p-series slash harmonic series. Harmonic series is just this particular p-series when p equals 1. Okay, the next one we have is called a alternating series test for convergence. So notice how here it says test for convergence. This is not a test for divergence. This test doesn't tell you if the series is divergent or not. It only tells you for sure whether the series converges. And the way you test this, so first of all, alternating series, what that means is that your terms are alternating back and forth between positive and negative terms. And what you're trying to figure out is, do my terms alternate in such a way that as I add them, those terms are getting smaller and smaller, so that means my sum is approaching some value. That's what you're trying to figure out. And so an alternating series is convergent when two things happen. The first thing that needs to happen is that your next term or your subsequential terms throughout the series are getting smaller and smaller compared to the previous term. So what that means is that if a sub n is the current term where you are, the term right before where you are, like the previous term that you just left from or that you just were at, should be larger than you. Or, in other words, your next term that you're about to go to should be less, meaning your series, the values themselves are decreasing each time. So what that means is that a sub n plus 1 is less than a sub n. So if you think about plus 1 is the next thing that happens. The next thing that happens should be less than the previous thing that happened. A sub n, you can kind of think relatively to where you are. A sub n is what already has happened. What's the last term right before where you are? N plus 1 is the next thing, should be less than the previous thing. So what this means right here, this inequality is basically saying is that the n plus 1th term, the next term, every single time you keep going to a new term, is going to get less and less and less. And so you have a strictly decreasing sequence of terms. So that's the first thing you need to check for if you're going to have convergence. The second thing you're going to want to check for convergence is the limit of a sub n. So I'll put and the limit as n approaches infinity of a sub n should be equal to 0. This limit has to equal 0 in order for this alternating series to converge. So notice how right here I'm taking the limit for a sub n. A sub n is whatever else is here. When you recognize or when you see some series, if it is on the test, if it looks like this, where there's a negative 1 to the power of n or negative 1 to the power of n plus 1, that's an alternating series. So what you're going to do is you're going to disregard this stuff right here. Just look at what else there is aside from the negative 1 to the power of n. And just take that a sub n, that general term, and take the limit of it as n approaches infinity. If the limit of that is equal to 0, and you have that the terms are decreasing after a certain point, then you'll know for sure that this alternating series is convergent. Okay, those are the two things you need to check for. For a ratio test for convergence, once again, look at the vocabulary here. Ratio test for convergence. When you're doing the ratio test, you can determine if the series here will converge or diverge. This is more general. This is kind of hard to identify. Just put a general a sub n here. A ratio test you can kind of use if some of the other tests don't work. So right here, the way we determine if a series is divergent using the ratio test is we set up this limit right here. Okay, if you notice in all of these divergent, convergent, and inconclusive, we have the same limit set up here each time. It's this fraction a sub n plus 1 over a sub n. So a sub n, this is the original thing that you see here, not including the summation. Just whatever stuff is right here, you put in the denominator. And then right here, wherever you see an n, you're going to put an n plus 1 in parentheses, and you put that in the numerator here. And you try to evaluate this fraction with absolute values around it. Okay, you have divergence if that limit is greater than 1. You have convergence if that limit is less than 1. And this test is inconclusive if the limit equals 1. If the limit equals 1, then you need to try one of the other tests that are on this page. So this is the ratio test here. You're just checking what does the limit approach. Is it 1 greater than 1, less than 1, or equal to 1? That'll tell you whether you're divergent, convergent, or inconclusive. Okay, the last section that's going to be here is called the Taylor series polynomial approximation. This one is probably the most expected one that I would see on the test because it's a big topic. Basically what a Taylor series is it's a series that estimates what the graph of some other function will look like around a certain point. It's not an exact function, but you can use this function to figure out what some other function might look like. And it's not exact, but around a certain point it's very close. And so if you look right here, there's this general term right here. So in general, for any function f of x, that function is approximately equal to the summation of this guy right here. Now what all this means is, right here, this first piece, f with this little k in parentheses, k is just the term that you are at, that number, so you start at 0, and in the parentheses here, it tells you which derivative you're at. So for the first term, you'd be at the original function. So the original function evaluated at some c. The c is the center around where you're approximating the function, the point around which you're approximating the function. So you plug in that c there. K factorial is whatever value you are currently at in your current term, the index, and then x minus c to the power of k. And what this looks like expanded out is a polynomial when you use a particular function. F of c, you're plugging in something into the original function. F prime of c times x minus c. The reason why this is like this is because this would be like, this first one would be the 0th term because k starts at 0. So you would divide by 0 factorial, which is 1, and you would do x minus c to the power of 0, which is 1. So that's why an f of c shows up here. Then you move on to k equals 1. Let me write that right here. So this is k equals 0. Then when you have k equals 1, that means you're at your first derivative. So f prime of c divided by 1 factorial, k factorial. So that's why I didn't write the 1 there. And then x minus c to the power of 1. So that's just x minus c. Then you go to the next term, where k equals 2. So this guy right here, here's k equals 2. If you notice, f double prime, second derivative, because k equals 2, divided by 2 factorial. x minus c to the power of 2, because k is 2. And then you can continue to add more terms to this. And the next one would be k equals 3. You can go on and do more terms if the problem asks for that. Usually the problem will ask for a certain degree polynomial. They'll say, write the third degree polynomial, Taylor polynomial for this function. So the third degree would be the term that has a 3 as its exponent. And so based on the problem, it'll ask you how many of these terms to write. You can keep going on forever. The more you go on, the more accurate your function will look. And the less terms you have, the less accurate your approximation is. After all, this type of a function, this polynomial meaning a series of terms with exponents, is an approximation. Okay, so I will work examples with Taylor series as well as the other series on this page, and I'll try to focus mostly on the terms that are the topics that are in this study guide.